Okay, in this video we are going to go ahead and get started with homework 4 for process dynamics and controls. So this is just part A, and what we're doing today is we're going to be looking at an example problem with a manometer. So we're going to go ahead and derive the transfer function, as well as simulate a little bit in Python. And then I'm going to explain kind of why two first-order systems in series always have a damping coefficient greater than 1 and are overdamped, and I'm also going to simulate the behavior of a second-order system. So first I'm going to get into that manometer example. I went ahead and drew this out beforehand, but basically we are assuming that the viscous damping in a manometer can be expressed in terms of the pressure drop associated with laminar flow, and we want to derive the transfer function relating the height difference between the fluid levels in a manometer to the pressure differential. So what I have on the left is a manometer with no significant pressure applied, or no, outward forces. And then over here on the right we have an atmospheric pressure applying downwards on the right side of the manometer, and this causes the fluid level to decrease on that side, and obviously it'll have to increase on the other side of the manometer. So I kind of drew this because this is the raised level, because before it was down here, and then this H is the level that that the right side decreased. So we know overall that the forces should be equal to the gravity plus atmospheric pressure. And I'm just writing plus. Some of these will be negative, but we'll take that into account later on. And then plus the viscous drag, and that is the drag of this liquid against the manometer walls, whatever material this is made of, probably glass. So gravity, as we know, is equal to negative mg. We are saying negative because it is pulling down on our system. We know mass is equal to the density times the volume, so we can write this as the density times the volume times gravity, and the volume is the area times the height, so we can also write this as negative rho A H G. And for the atmospheric pressure, we know that a pressure is equal to the force applied per area. So if we have an area, we would have a force being applied. That would be the pressure. We can rewrite this in terms of our force and say that is equal to the pressure times the area. For the viscous drag, this is the more complicated one, so we are going to call this a negative K times dH dt, where the K is some resistance value. And then this dH dt is the change in height over time, and this would be liquid level height inside the manometer itself. So as of right now, we have F is equal to negative rho A H G plus PA minus K times dH dt. For the purposes of this video, I'm going to go ahead and ignore the potential and kinetic energy that we would normally use in the Bernoulli equation. But we would have a delta P, the change in pressure, over the density is equal to 4 times the fanning friction factor, which I'll get into in a minute, times the length over the diameter, times the average velocity, divided by 2, and that's squared. That is the average velocity squared over 2. The fanning friction factor this F sub F is equal to 16 over the Reynolds number. Our Reynolds number is rho VL divided by mu, so that's the density times the velocity times the length divided by the viscosity. So this would be 16 times mu divided by rho VL. And then with these two densities, they'll cancel out, and we'll be left with delta P is equal to 4 times 16 mu over VL times L over D times the average squared over 2. So we can go ahead and simplify this further. We have 4 times 16 divided by 2, so that is 32. We have mu times L, and that is going to be over the diameter squared, and we are multiplying by dH dt. And earlier when I said dH dt is the change in height over time, that is true, but also this is the fluid velocity. Because remember, we were talking about this fluid length and this height here. So as that height changes, that describes its velocity, the flow velocity. We then can multiply by the area, so we'll be left with PA is equal to 32 mu L pi times the diameter squared over the diameter squared times 4. And this is multiplied by the average velocity. As we said, that is what dH dt is. And this leaves us with 8 pi mu L times V average. And this right here is actually that K value I talked about up here. Basically, that's what we just solved for. So we still have this equation that I wrote above, but now we know what K is, so we can write this a little bit more thoroughly. So our force is equal to negative 9.8, that's gravity, times density, area, and height. And then we're adding the pressure times the area, because we've denoted that direction to be positive. And then we're subtracting K, so that's 8 pi mu L times dH dt. Remember, dH dt is our average velocity that we talked about. We also know that force is equal to mass times acceleration. mass times acceleration. In our case, it's helpful to write it as rho times a L. Then it's the second derivative of the height with respect to time, because we are talking about acceleration rather than just velocity. Now we can divide by rho a L to get that term by itself. So we have that force is equal to negative GH over L plus P, our pressure, over rho L minus 8 pi mu divided by rho A times dH dt is equal to our second derivative on the right hand side. Remember that this is second order. And for ease of writing this out, I'm going to set a beta value equal to 8 pi mu over rho A. I'll also set another variable, gamma, equal to G over L. And I think we want to also do 1 for 1 over rho L, and let's call that alpha. And I'm going to go ahead and rewrite this with those terms. So we have F is equal to this right here times H, and we're going to add our alpha times pressure, subtract beta dH dt, and set that equal to that second order derivative on the right hand side. What we're going to do is we're going to set this equal to our alpha pressure. So we have our d squared, or not d squared, the second derivative of the height with respect to time, so that's our acceleration. We are going to go ahead and add gamma h as well as beta dH dt. And that, as I said, is equal to alpha times the pressure. And when we do our Laplace transform with the Laplace domain, we get s squared h. So this is from the term directly above, plus gamma times h. Remember that this capital H denotes that this is in the Laplace domain. And we also need to add beta, and this is dH dt, so that leaves us with sh. Remember that this is s squared on the left because that was a second order derivative. And this is still equal to alpha p, but the p is in the Laplace domain, so the p I have above is already a capital P, so I'm just going to make it bigger, but just know that it is now in the Laplace domain. And we notice we can pull out our height, which is what we wanted to do, so we have s squared plus gamma plus beta. Now I'll actually rewrite this with the beta term in the middle. So we have s squared plus beta s plus gamma. Remembering that I just set these equal to those values in green, blue, and red because there are a lot to write down. But that is equal to our alpha times p. Then we isolate our h. We get h is equal to alpha divided by s squared plus beta s plus gamma, and this is all multiplied by our pressure. This is a second order transfer function, and that is because of our s squared term. So the standard form for a second order function like this would be something like GP is equal to K divided by tau squared S squared plus 2 zeta tau S plus 1, and this is something we'll be using in the code later on, but our K would be equal to alpha over gamma, tau is equal to the square root of 1 over gamma, and zeta, and I'm probably not drawing zeta correctly, but zeta is equal to our beta divided by 2 times the square root of gamma. And this zeta is the damping coefficient. So our goal was to derive the transfer function relating the height difference between the fluid levels to the pressure differential, which we have done right here, remembering that all these Greek letters are defined up here. For now, since I want to get all of the deriving and just writing on my iPad out of the way, I'm going to go ahead and skip the next part and come back to it when I'm done with this here. So this is technically the third thing we're doing, but I will go back and do the second when I go onto my laptop and start coding. So one thing we want to do in this video is to show algebraically that two first order systems that are in series will always have a damping coefficient, our zeta, greater than 1 and is overdamped. For ease of showing this, I'm going to do two first order transfer functions. That's just going to be K1 over tau 1 S plus 1 and K2 over tau 2 S plus 1. And they could look a little bit different than that, but this is our most kind of simple case. I guess the most simple case would be if these two were the exact same, but just for the purposes of this video, I am going to do it this way. So with them being in series, we would multiply the two by each other. This is our process transfer function for the system. Tau 2s plus 1 is equal to K1 times K2 divided by tau 1 tau 2 s squared plus tau 1 plus tau 2 times s plus 1. Now if we set our tau equal to the square root of tau 1 times tau 2, that is our geometric mean. We have tau 1 plus tau 2 is equal to 2 zeta square root of tau 1 times tau 2. And solving for zeta, we have zeta is equal to tau 1 plus tau 2 divided by 2 plus that geometric mean. And this right here is our damping coefficient, zeta. And what we want to do is prove that this will always be greater than 1. So one thing that we know is the arithmetic mean is going to always be greater than or equal to the geometric mean. And by that I mean we would have, when you're generally taking the mean, you would have it be like this, and eventually we end up with tau 1 squared minus 2 tau 1 tau 2 plus tau 2 squared is greater than or equal to 0. And what this means is the arithmetic mean is always greater than or equal to the geometric mean. Therefore, our zeta is always going to be equal or greater than or equal to 1. This should be true, and so it should be overdamped. Now I'll get into the code that I skipped prior. Basically, we're going to code up an example for the manometer example, and then after that, I'm going to simulate the behavior of a second order system for different damping coefficients to kind of display what those mean and how that affects a system. I went ahead and took our usual import. I also commented out these alpha, beta, and gamma values so that I don't forget what where those came from and what they are. So just going and getting started, we know our gravity is equal to 9.8, that's meters per second squared. I guess I should show you first what we're doing. So for a water-filled manometer where the total length of fluid is 1 meter, with a tube diameter of 1 centimeter, we want to determine the gain, damping coefficient, and time constant of the second order system. As we talked about, it was second order. We had that f squared term in the transfer function. And we also want to simulate the response of the system to a 5,000 Pascal step change in pressure. So there's a few things that we want here. As I was saying, I have my gravity, our rho, that's 1,000. This is kilograms per meter cubed, and that's for water. We also need the length. We have length of 1. Mu is 1 times 10 to the negative third. That is the the dynamic viscosity of water. I'm just going to set pi equal to 3.14. The diameter was 0.01, so that's 1 centimeter. And our area is equal to pi times the diameter squared divided by 4. So that's the cross-sectional area of our manometer. It'll look like a circle, but we have the manometer like that. And actually, I should be able to take my commented values from above to calculate my alpha, beta, and gamma. As I said when I was deriving the function earlier, our k is equal to alpha divided by gamma. Our tau was equal to 1 divided by the square root of gamma. And we also said that zeta was equal to beta divided by 2 times the square root of gamma once again. And we want to get k, tau, and zeta for this problem. We want to get our gain, which is k, the damping coefficient zeta, and time constant tau. So let's run this and see if it gives us values. All right, so right here we have our gain. It's about 0.0001, so quite small. Our tau is 0.32 roughly, and our zeta is 0.05. So what this means is that our zeta is 0.05, meaning unlike what I just showed in technically the third part, this is not overdamped, this is underdamped, so we will be seeing oscillations when I code out the simulation. And just to show you a quick example, we have underdamped up here, which is what we'll see oscillations. Critical damping means we get to our point pretty quickly. Overdamped means maybe the system has a lot holding it back, kind of, so it might not reach that point, or it might take a very, very long time. Here's another example of that. So now we would like to simulate the response to a step change in pressure. we need to put our transfer function down that I derived earlier. It was k divided by tau squared times s squared plus 2 times zeta times tau times s plus 1. And now we want to simulate, so we're going to take that transfer function and I'll explain what this means. And I forgot to put that right there, but 5 times 10 to the third, that is our 5,000 Pascal step change. This defined our dt, and that's how many times we're going through this calculation. We want to make subplots and add a scatter where x is equal to time, y is equal to the height, and we're going to name this height difference manometer. And I'm going to go ahead and update the layout as well. I'll go ahead and delete that, and I'll just add this title here, manometer response to 5,000 Pascal step change. The x-axis title should be time in seconds. And the y-axis title is the height difference, and this would be in meters. And then we would obviously like to show our figure. I'll go ahead and see if this can run. And here is our response to that pressure step change. And as you can see, since we are underdamped, we see those oscillations. They eventually calm down and stop around 0.51 as the height difference. But as you can see, it heavily oscillates towards the beginning and doesn't really calm down until about 30 seconds in. Obviously, if this was a larger value, we would see huge oscillations, which would be obviously problematic. This is what we have here. So yeah, we simulated the response to that step change in pressure. With it being underdamped, lots of oscillations. And what we want to do next, since I already showed algebraically that two first order systems in series always have a damping coefficient greater than 1, I'm going to move on to this fourth part where I need to simulate the behavior of a second order system for different damping coefficients for oscillatory inputs at frequencies below, at, and above the natural frequency. I actually went ahead and had Gemini help me write this out because I wasn't sure like the best way to, I guess, like display this information. So what I'm going to do is go through it as best I can, and then I'll run it and I'll show the output. So we just set a gain and time constant of 1. This Wn is the natural frequency, which is our 1 over tau. And we wanted to test underdamped, so a zeta of 0.2 is underdamped, that's below 1. Critically damped means it's at 1, so it's perfect. And overdamped, 2, obviously 2 is greater than 1. So those are our test values there. And we also wanted to test below, at, and above the natural frequency, which we defined up here. So we have that there. 1.0 is at resonance, so kind of similar to the zeta. And we did a nested for loop, so for zeta and zeta values, and for mult and frequency multipliers, omega is equal to the multiplier times our natural frequency. This is our transfer function, and we wanted to simulate the response to an oscillating input, so we just did sine of omega times t. Remember, the omega is our multiplier times the natural frequency. So that's how we are testing below, at, and above the natural frequency. And similar to what we did above, we simulated over some time with our sine input, made our subplots as per usual, added our scatter where our x-axis is the time, our y is that sine frequency, and we have an output where we're looking at the height. And this is where I wasn't sure how to code it for myself, but we have our title set right there. And if I run this, we should get a few graphs that we can look at. So let me go and see. So this example is the damping coefficient of 0.2. So we're looking at the underdamped, and we're also doing a frequency ratio of 0.2. So we're testing below the natural frequency. As you can see, the input and the output aren't too mismatched or anything. And as we go down, when we reach the resonance frequency, our output exponentially just grows. So here our output has grown a lot more than the input. Remember, the input is a sine wave, so it's oscillating between 1 and -1, which we can see here, but the output is much, much larger, more than 2 times. And then again, with still being underdamped, with the same damping zeta value, but with a high frequency ratio, our output is very, very small. And continuing, if we look at our critically damped scenario with a low frequency ratio, the output shifts very slightly. But if we have our resonance frequency, again, we see, well, actually different than what we saw with the underdamped. The output is actually a little bit smaller than the input. And if we take a look, it is at about half of what the input was, being at 1 versus 0.5 or so. And when we have that high frequency ratio, it's similar to what we saw previously. So when we have frequencies above the natural frequency, that's when we see these this output really shrink. Here we have our overdamped scenario with the low frequency ratio. Now we are seeing shifting and a little bit of compression, but when we go to our resonance frequency, our output shrunk even more than when we had the critically damped scenario. And then here, again, our output is very, very small. So this would not work very well. That's all I have for this video. Our next video, part B, is going to be looking at the Bode frequency stability analysis. Thank you for watching, and I'll see you in the next one.